Could everyone hear me? Good evening. Welcome to People's University. If you wouldn't mind turning off your cell phones now, that would be terrific. Couple announcements. Next week at Lunch with Books on Tuesday at noon, Fair May. We're going to do another tribute to St. Rocco, San Rock, along with the folkloric dance ensemble. So they do Italian dance. That'll be the 15th at noon. And on the 22nd at noon, that mural you saw coming down, we're going to celebrate that and Vondell Bell's accomplishment as the artist. We'll have music. We'll see a time-lapse video of him making that mural. And we'll have food. Very good food. Do not miss it. That'll be on August 22nd at noon. Next Thursday, Class 2, the question is, will forests continue to slow climate change in the future? And our instructor for that one is Joanna Ridgway, who's a PhD candidate in the Department of Biology at WVU. So, why are we here? Well, this is part of our effort called Wheeling Reads. And if you don't know what that is, Wheeling Reads One Book, One Community is designed to bring our city closer through the shared experience of reading and discussing the same book. And the book is Jennifer Haig's Heat and Light, which tells the story of a western Pennsylvania coal town that finds new life as a fracking town. So that's why we got on the subject of the impact of fossil fuel extraction and burning. And our festival for that book will take place on September 9th in this room. That's a Saturday. Jennifer, the author, will be here. We have 3 workshops in art, poetry, and young adult fiction with very fine workshop leaders. So I encourage you to take a look at the brochure and the signs that are on your table. If you haven't read, who is reading Heat and Light? Okay, good. How many plan to read it before then? Okay. We have unlimited copies on something called Hoopla, so these would be ebooks or audiobooks. If you go to our website and look for Hoopla under our downloadables, you can listen to the book anytime. We also have hard copies, and you can put a reserve on those. I have given away several hard copies, so I'm going to try to do that again, so look for that. So why the subject? Well, the hottest month on record by humans is July 2023. And this year is on track to be the hottest year of record. Recently we had smoke, you'll recall, descending from Canada, of all places. And all over the globe we see stronger, more frequent storms, tornadoes, hurricanes, flooding. You know the story, you see it on the news every night. Maui is currently burning to the ground. Everyone seems, you can't disagree, it's happening. Climate change is not an opinion, it's a fact. This disagreement comes about whether humans are causing it. And so that's why we're here. We're here to ask, what, if anything, can we still do? And do we have hope? So that's what the series is about. Our instructor this evening is Dr. William Peterjohn. He is a professor of biology at WVU. During his 40-plus year career as an ecosystem ecologist, his research has focused on the interface between terrestrial nutrient cycles and human-caused changes in the environment. He received a BS in mathematics and biology from Baldwin Wallace College, a master's of environmental science from Miami University, and PhD from Duke University. Prior to arriving at WVU, he worked for the EPA for one summer, the Smithsonian Institution, and the Ecosystem Center in Woods Hole, Massachusetts. During his career, he's conducted research in agroecosystems, deserts, and the forests of West Virginia. Here's Dr. William Peterjohn.
Well, thank you so much. This is the time when you're thinking to yourself, he doesn't look that old. But thank you so much for inviting me, and it just really is a pleasure to see so many people coming out to listen to something about climate change. And since this is the first talk in a series that you're going to be having on this subject, I thought I'd take this opportunity to provide you with a very broad overview that touches on three aspects of climate change: the causes of climate change, the consequences of climate change, and some of the challenges we face with respect to climate change. If I can get the projector to work. So, I'm going to start by talking a little bit, maybe too much, about the causes of climate change, about how the planet, in this case planet Earth, regulates its temperature or establishes its temperature. And the reason I want to talk about the causes of climate change is simply because we're not going to know what to do if we don't understand what's going to go on. So what controls the temperature at the surface of Earth? And fairly simply, it's the balance. It's the balance between absorbed sunlight that will warm things up and the loss of energy as earthshine, if you will, or earth light, which is infrared radiation that the Earth emits back to space. And perhaps it's easiest to understand if we kind of take a very simple conceptual model of a kitchen sink. And here what we have is sunlight pouring energy into the kitchen sink, or water into the kitchen sink in this case. But not all of that water stays in the sink. Some of it splashes out. And that happens with sunlight on our planet as well. And here's your one kind of technical term. That splash is what we call albedo. Not libido, albedo. And albedo is simply the fraction of sunlight that is reflected back to space without ever being absorbed and therefore never causing any heating of the planet. And about 30% of the sunshine currently that strikes the top of the Earth's atmosphere is reflected back to space with never having been absorbed. So that's the flow of energy or water into our kitchen sink. And then we have the flow of water going down the drain. And that is the radiation being emitted by the Earth. It turns out that any object with a temperature emits radiation. And it's the intensity of radiation and the type of radiation that it emits is a very sensitive function of its temperature. If you increase the temperature of an object, it radiates more intensely. So this drain is linked to the temperature of the object. And then, of course, the water level represents the temperature, how much heat has accumulated and is warming the Earth. Now, we're going to start simple. So we're going to start with a naked planet. A planet with no atmosphere, no greenhouse gases, and we'll see where that gets us. If we plug in realistic values for the amount of sunlight striking, the amount that splashes out of our sink, and the temperature dependency of these radiation emissions by the Earth. And it's not a difficult calculation. We won't do it, but it's not a difficult calculation. If we do it, we get a temperature of minus 18 degrees Celsius. Minus 18 degrees Celsius would mean that all the water on our planet is frozen and we'd have a lifeless planet, so there's something wrong with our model. And so there are other features. Get this to work. There are other factors that affect the surface temperature of our planet. And if you're running around naked and you're too cold, you may want to think about putting some clothes on. So we're going to modify our model just a little bit, and we'll call this the partially closed kitchen sink model or planetary model. And we're going to put a little clothes on this planet in the form of an atmosphere that contains special gases called greenhouse gases. And what these gases do is that they slow the loss of Earth light, or that infrared radiation, back to space. So I'm going to try something fancy here and see if I can enlarge it. So in our kitchen sink model, it's as if little bits of carrot had kind of partially obstructed the drain, slowing down the loss of water through the drain. And what happens initially when you do that is, well, the water pouring in is pouring in faster than it's now going out, and so the water level increases. And in the case of the planet, the temperature will rise until the downward pressure of the water forces the water down the drain at a rate that matches, comes into equilibrium once again with the flow of water in. And that's what happens with the temperature of the planet, because this Earth light, the intensity at which it radiates back to space, is a sensitive temperature, is a sensitive function of the temperature. We raise the temperature, it's going to increase the amount of energy loss until it once again matches incoming sunlight. All right, so that's our fancier model, our partially clothed model. And if we put realistic values in, again, for the sunlight and the albedo and greenhouse gases now in the atmosphere, it accomplishes what we want it to do. It warms it up above freezing. Our planet is no longer frozen. But, and so that's sort of it. It does good things, but the problem is that the temperature that you calculate is too hot. 63 Celsius, put that in a more contextual, it's 145 degrees Fahrenheit. So we've improved it a little bit, but then we've made it worse. So we need to spruce things up and polish up our model a little bit more. We need to add a little more complexity to our model, and we need to do that by incorporating factors that will cool down the surface. Let's see here. So we need to add some more bells and whistles, and if we want to make our model look really cool, in addition to just greenhouse gases, we can really dress it up and give it the full Cleveland treatment. Now, I never knew what full Cleveland meant, except my postdoc advisor mentioned it, and I'm from the Cleveland area. And so I had to Google it and looked it up, and then this is what I found. It's the full polyester leisure suit, it's the white belt, it's the white patent leather shoes, it's the bog lapel, let's throw in some sunglasses and a gold chain and a hairy chest, and you're all set. So, we're going to really dress this model up in order to be cool, right? But to be cool at the surface of the Earth. So we're going to add more bells and whistles, and what we're going to do is add factors that will cool off the surface, and many of these factors are things that you would do if you wanted to cool off on a really hot day. One thing you might, if it's too hot in the kitchen, if you can't stand the heat, get out of the kitchen. So one thing you might do is go in the shade, and it turns out that there's materials in our atmosphere that actually absorb sunlight and prevent it from reaching the surface of the Earth. So it's providing some shade, so to speak, to the surface. It warms the atmosphere, but cools off the surface a little bit. Another thing you might do, if you have a really heavy blanket over and you're too hot, you might rip some holes or cut some holes in the blanket. And it turns out there are some holes in our atmospheric blanket as well. So if we look at our little attempt at a diagram here, there's a small amount, about 4% of the radiation the Earth is emitting back towards space, goes directly to space and doesn't interact with those greenhouse gases at all. So it's like we punch a little extra hole in the bottom of our kitchen sink, but a drain that isn't clogged or interfered with by greenhouse gases. That radiation just goes directly to space. And I should mention about 25% of incoming sunlight is absorbed by materials in the atmosphere and shades the surface. So those are two things that can cool off the surface. Yet another thing is heat transfer. And you might, if you're hot, you might stand in front of a fan, or you might fan yourself, and the circulation of that air will carry heat away from you and cool it. And the same thing happens at the surface of the Earth. The circulation of the atmosphere will convectively mix heat away from the surface and dump it into the atmosphere, cooling off the surface to some degree. And the final thing you might do is you might sweat. And the surface of the Earth, metaphorically sweats as well. Water evaporates, and the energy needed to evaporate that water is carried away in the form of water vapor from the surface and is deposited once again in the atmosphere when that water vapor condenses. So we have all these processes that we need to add to our model. We need to add kind of holes in the blanket, we need to add shading, we need to add kind of fanning effect of circulation in the atmosphere, and we need to add sweating. And when we add all those features in, again, it's not terribly difficult to do, but if you do that in this very simplistic model and calculate what the surface temperature is, it comes out just right. comes out to 15 degrees Celsius. And this is the average temperature of our whole surface temperature of our whole planet. Obviously, it's warmer some places and colder others, etc. Now, these features that can affect the energy balance of our planet and thus its temperature are what we call climate forcing factors. So if the sun gets brighter, that can affect our climate. If more water splashes out of our sink, that'll affect the level of water in our sink. Or so if albedo, if our planet becomes shiny or less shiny. Greenhouse gases also, whoops, got ahead of myself. Greenhouse gases also can affect this climate. And so changes in these things can force a change in the climate. And if they stay constant, the climate stays constant. If some change and others change in ways that offset it, counterbalance it, then the climate stays relatively constant. But we know that our climate has been temperamental. And in other words, it's changed in the past as a result of these climate forcing factors changing. And these climate forcing factors can be natural changes, we get more volcanoes erupting or ice sheets forming, or they can be human-caused changes, like the burning of fossil fuels and the addition of CO2 to the atmosphere. And we know that climate is temperamental and has changed in the past because we can see it. We can see it in records of ancient climates. And that's an example of that is shown here. If I can zoom in. And what we're looking at here is a record of past conditions on our planet over the last 800,000 years. Let me orient you. We're pre-industrially, we're right here at 0. Is that showing up? No, it's not even showing up. I'm pretending like this pointer is working. It's not. Anyway, we're starting over here, and we're going backwards in time for 800,000 years. And the light blue line is the temperature. And you see it's going up and it's going down. It's warmer, it's colder, it's warmer, it's colder, it's warmer, it's colder. And the dark blue line is the carbon dioxide concentrations. Now, this is from an ice core. This is from Antarctica. It's amazing that we can even do this. And we have chemical signals in the water itself that we can reconstruct the past temperature. We have little bubbles of air that we can crack open at various depths in the ice core and analyze them for the various greenhouse gases. The deeper you go in the ice, the further back in time you're going. And we have ways of sort of dating where we're at in the ice core. And they've reconstructed this record. And the things I want to point out, first of all, that the warm, I keep doing that because it's not, the peaks are interglacial periods, and that's what we're in right now, relatively, comparatively warmer periods. The valleys are glacial periods, when large ice sheets covered Wisconsin and part of Ohio and Scandinavia and Northern Europe and Canada, etc. Okay? So what we're seeing here is a record of this sort of periodic warming, interglacial, glacial, interglacial, glacial, interglacial, glacial. The other feature to note is the synchrony, the close association between the concentration of the greenhouse gas carbon dioxide and the climate. When it was warmer, CO2 was higher. When it was colder, it was lower. When it was warmer, it's higher. When it was colder, it was lower. Now, in the case of glacial, interglacial features, we know that it's not CO2 that triggered this. What triggered this is actually wobbles in the Earth's orbit around the sun, but those wobbles that kind of redistribute the intensity of sunlight across the Earth aren't strong enough to drive this type of climate change. But what CO2 does is it amplified that in this particular case. So it's a strong amplifier for glacial, interglacial climate. So it contributes to sort of an important feedback loop. Now, we can look back even further in time and see what lessons we can learn from that. If I can get this zoomed in here. Okay. So at the top we're going from kind of you are here, present day, back in time, and now this time, and this is reconstructions of CO2 levels, we're going back 400 million years as best we can. And below it, doesn't go quite that far, but is reconstruction of past temperatures going back 60 million years ago. And what we see, if I can get this both on the same screen, I practiced on a Mac, what can I say, this is a PC, and I'm still trying to use that pointer. What we can see is that times, starting here 60 million years ago, when CO2 went up, temperatures were higher. When CO2 started to slope down, temperatures got cooler. And then we go through the wiggles of the glacial, interglacial cycle. And then we come out 10,000 years ago, the scales are chunked into different intervals of thousands, millions, hundreds of millions. But since about 10,000 years ago, we warmed up from the last interglacial glacial period into the current warm interglacial. And you see a flat line in CO2. And you see a relatively flat line in the lower graph in temperature. So for the last 10,000 years, our climate has been relatively stable. And that's an important point, because our civilization, by one measure, is about 10,000 years old. If you define civilization as, like the oldest cities, some of the oldest, like Jericho is one of the oldest cities, about 10,000 years ago. It means the entirety of our civilization was emerging under a relatively stable climate. And then if you look at the top graph, you'll see a little arrow that says Homo sapiens. About 200, 300,000 years ago is the first evidence we have for the appearance of our species. And on the line where it says you are here, there's a dotted line that goes across. It says 400, it's now 417, present day levels of carbon dioxide. And what that means then is that present day levels of carbon dioxide are higher than anything our species has ever experienced. Our civilization, our species, and we know from ice cores as well that our present day levels are higher than anything in the last 2 million years. So that takes us back to around the time of our genus, so that includes Neanderthals, Homo erectus, and others. Okay? So I bring this up because you'll hear a lot of times that, well, climate's changed. So if we're causing it to change, no big deal. It goes up and down, it varies, it's cyclical. And that's true, but it's not really relevant, since we now have increased CO2 levels and we're increasing the temperature to levels that society, civilization, our species, our genus has never experienced before. Yeah, if you want to go back to 400 million years ago, things may have been warmer, but does that really relevant? Let's see, what else do I need to, I think that's what I want to say about this particular slide. Oh, and the things off onto the far right here, you're right, you see the lines kind of going up, that's potential future. Okay, that's, we don't know how high CO2 is going to get in the future, it depends on what we do, but they run various scenarios, and so you can see we can get CO2 levels high enough that it would take us back to hundreds of millions. The last time we had levels that high back to 100 million years or more ago. And on the lower graph, those are the projected temperatures that we might get to if we increase greenhouse gases to that extent shown above. So the Earth's climate is temperamental. So in contrast, though, to the last 10,000 years of relative stability in Earth's climate with respect to CO2, with respect to temperature, things have started to change. And the change started around the end of the 19th century, the 1850s, 1880s, around the time of the beginning of the Industrial Revolution. And we see that the Earth's temperature has increased since that time, and we know that we're to blame. I won't mince any words about it. And we notice that the temperature is changing because we've increased greenhouse gases and CO2 in particular to levels that the Earth hasn't seen for 2 million years, at least. Now, if we look at the actual record, that's what's being shown here. These are thermometer measurements. And they've been corrected for a variety of potential biases and other issues with them, so it's the best we can do. And what it's showing is that the temperature, I keep doing that, the temperature has gone up. Ooh, shadow, yeah, ooh, yes. So the temperature has gone up, and it's gone up about 1.2 degrees Celsius since pre-industrial times. But you also notice that it hasn't gone up in a straight line. Okay? It hasn't been a steady increase. Rather, we have this little increase. We have a period of 30, 40 years here where it may have even cooled a little bit or stayed flat, and then it went up again. Okay? But we know what causes this pattern. And the causes is primarily the increase in greenhouse gases in the atmosphere, along with some of those other forcing factors. You know, the fact that the temperature here remained relatively flat, despite CO2 and other greenhouse gases going up during that time, doesn't mean that CO2 doesn't have a warming effect on the planet. It means that other things affect climate besides greenhouse gases. And some of them cool the planet, can offset that warming effect of greenhouse gases, at least for a period of time, and that's what we think happened. So scientists have been busy examining all these possible forcing factors, you know, other things that might change the climate besides greenhouse gases. And so what we have here, the dark line, is the record you just saw. That's our instrumental record. That's what we know went on. If we put in natural changes, volcanoes erupting, wobbles in the Earth's orbit around the sun, changes in the extent of sunspots, the brightness of the sun, we put them in the model, either the effect is too small to account for this increase, or it's in the wrong direction. It has cooling effects. But if we include human climate forcing factors, greenhouse gases, as well as aerosols, which have a cooling effect, and we do the math, we find a fairly good agreement between the overall trend, which is the black line of observations, with our understanding of the climate. And importantly, no one else has come up with an explanation that works. That when you do the math and you put it in, can reproduce what we've observed. And conversely, no one else has come up with a reason why our current understanding, which seems to work, shouldn't work. So we're fairly confident. If we have time afterwards, there's more empirical evidence for why we're to blame. But this has been sort of called smoking gun evidence. We're very confident that it's the result primarily of the release of greenhouse gases by human activities that has caused this 1.2 degrees Celsius warming that we have observed. So, if CO2 is so important, and if human actions are increasing the levels of CO2 in the atmosphere, what happens to that CO2 that we add to the atmosphere? And the answer is that Mother Nature will clean up half of our mess, or is cleaning up half of our mess right now. If we look in more detail, we see that of our emissions of greenhouse gases to the atmosphere, CO2 in particular, about 89% is coming from the burning of fossil fuels, about 11% from the net destruction of forests, primarily in the tropics. What happens to the extra CO2? Well, Mother Nature on land takes up about, we'll round it down, 25%, a quarter. The oceans soak up about a quarter. Okay. And the rest, the remaining half-ish, 48% if you want to be precise, is accumulating or building up in our kitchen sink, okay, of the atmosphere, is accumulating in the atmosphere. So Mother Nature is cleaning up some of our mess, but not all of our mess. But, there's always a but, the processes by which this happens, like photosynthesis or the dissolution of CO2 in ocean water where it reacts with carbonate and gets hidden in molecules called bicarbonate in the ocean, those processes can saturate. They can slow down. And if that happens, and then we have some suggestions that keep popping up that that may be happening, tropical forests may no longer be soaking up carbon, CO2 as much as they used to. If that happens, that extra CO2 we're adding is going to end up in the atmosphere and accumulate even more in the atmosphere, achieving higher levels in the atmosphere where it acts as a greenhouse gas, where it inhibits and slows down the rate at which Earth's radiation is lost back to space. And these elevated levels of CO2 in the atmosphere remain elevated for a long time. That's sort of the other kicker here. And that's what's being shown here. Let me zoom in. So if you take a bucket of CO2 and we throw it in this atmosphere, if we were to take all the fossil fuels we're aware of and burn them all at once, which is kind of what we're doing, and put that into the atmosphere, and then stop, the high levels of CO2 will drop to about 40% of those levels after 100 years. Will drop to about 20% of those high levels after 1,000 years. And drop to about 10% of those levels after 10,000 years. So the more we put up, the longer we're going to have to live with the consequences of 40% of that level, or 20%, or 10% of that level. Now, can Mother Nature clean it all up? And the answer is yes. But the question is, how patient are you? In order for Mother Nature to clean all of that up, it takes on the order of 500,000 to about 1 million years. Okay. So, that's kind of the fate of CO2 that we're adding into the atmosphere today.
But that's like if we stop burning, if we keep burning.
Well, yeah, if we keep burning, it's the kitchen sink. If we're adding it faster than nature can remove it, it's like your bank account. If you deposit money faster than you spend it, your bank account gets bigger. Okay? So we have to reduce emissions to levels below what Mother Nature is taking up, and we'll get into a little bit of that a little later. So having considered a little bit about causes of climate change, I'd like to consider a few of the consequences, and the list is many. Kind of stole my thunder in the introduction a little bit, but there are a lot of them, and I think they're pretty concisely described by Bill McKibben. And if you've not read Bill McKibben, he's a very talented writer focused on climate change, who created a book, or published a book in 2011 called Earth. And his explanation for why that title is the way it is kind of tells us a lot about some of the, get this to work, some of the consequences of climate change. And what he says is our old familiar globe is suddenly, see if any of this sounds familiar, melting, drying, acidifying, flooding, and burning in ways no human has ever seen. We have created in very short order a new planet. That is a new planet, still recognizable, but fundamentally different. We may as well call it E-Earth. And so being the clever author, you know, yeah, the title, you recognize that he's trying to say Earth. It's recognizable, but it's fundamentally different because he slipped in that extra A. So let me walk you through just a few of the long list of changes that have already happened and are still going on. Okay, so this is not model projections into the future. These are documented changes that we have already observed, and one of them, not surprisingly, is the world is warmer. We just saw that it's 1.2 degrees Celsius warmer than pre-industrial times, but it hasn't warmed uniformly. It's sort of warmed non-uniformly through time, but it's also warmed non-uniformly in space. So this is the actual temperature changes we've seen between 1901 and 2011. The warm colors means it's gotten warmer. And a few things to note here, a few patterns. One is that it's warmed up faster on land than it has in the, over the ocean. It's also warmed up more in the northern hemisphere than it has closer to the equator. And there are some areas that haven't warmed at all but actually have cooled off a little bit. So the Earth has gotten warmer, but not uniformly in space or in time. Perhaps more importantly is the nature of the warming has changed as well, in the fact that we are experiencing more extremes of temperature. So extreme temperatures have become more common. And a nice way of thinking about this is one that Jim Hansen, I'm trying to throw out some names of trustable sources of information, NASA climate scientist, now retired, but he noted that what we're doing is kind of loading the climate dice. In the period between, where's my pointer here, 1951 and 1980, the odds were pretty equal that any roll of the dice, any given year, you might have an average temperature for that period of time. And then about a third of the time, you might have a below average temperature, or a third of the time, an above average temperature. And so if you had a climate dice, you know, two sides would be white for normal, and two sides would be blue for below normal temperatures, and two sides would be red for higher than normal temperatures. And every year you're rolling the dice, and it might be a warmer year or a colder year, etc. But the odds have changed. When we get to the first decade of the 21st century, we see instead of two sides being normal temperatures, the odds have been cut in half. So one side now is what used to be normal temperatures. And the odds of having an unusually warm temperature. Now these are summer land temperatures in the northern hemisphere. Why are we being so restrictive here? Because summertime on land is when we grow our food. But we see the odds of having unusually warm have gone from two sides of the die to four sides of the die, have gone from a third to two-thirds. And we see the odds of having an unusually cool summer are lower. We also see a unique thing down at the bottom here. We see a color we didn't have before. We have temperatures, hotter temperatures, that we never experienced before. And that's what's being shown here. These are the actual distributions. And we're moving from, from this sort of equal parts of normal, colder, and hotter to a big shift over here where we're starting to see temperatures that we never saw before. Okay, well, we expect in a warmer world that the circulation of water will be changed and altered, and that's what we've seen. Okay, warmer temperatures means more evaporation. More evaporation means more water vapor in the atmosphere. More water vapor in the atmosphere means more rain. And overall, precipitation on land has increased, but not uniformly. Okay. And indeed, the world is becoming both drier and wetter depending upon where you are. And that's what's being shown here. These are the observed changes in precipitation globally. And what we see is that the green areas are where it's gone up and gotten wetter, and the dry areas are where precipitation has gone down. So there are large areas that are experiencing drier conditions, or less rainfall, I should say, in Africa and eastern Australia, in the western U.S. and southern and southwestern U.S., around the Mediterranean and parts of Asia, etc. So, like temperatures, it's patchy. You know, it's not every place is getting wetter or every place is getting drier, but it has a lot of important spatial variability depending upon where you live and what happened to my. Wow, so there it is. But a lot of buts. I know, sorry. But it's not just the amount of rainfall. Perhaps more importantly, it's the nature of rainfall that is changing as well. And what we're seeing is that heavy rainfall and the consequences associated with heavy rainfall are becoming more common in some places. And some places include the United States, where we're looking here at extreme precipitation changes over a period of time, and green means it's gone up. But particularly, we see an increase in extreme precipitation in the northeastern U.S. and really the eastern half of the U.S. We can look at this another way. Zoom in on this. And what this is going to show is we can take a 60-year period of time and look at the observed change. This is for the U.S. Observed changes in stream flow and precipitation, and rank them as light precipitation and low stream flow, moderate of each, or heavy precipitation and high stream flow. And this is the percent change of time. And we see in that 60-year period, all of the change has happened in the heavy and high. The heavy precipitation has gone up, the observed change, and the consequence of that is more flooding, higher stream flows. And that's something we're very familiar with in West Virginia. You get a heavy rain, this you can't see very well, but this is a bridge going into Parsons, West Virginia. That's the Cheat River, and after a heavy rain in April of, I can't even see it, around 2018, and it's almost breaching the bridge. Okay. So it's not just the amount of precipitation, but it's how it's delivered. You know, if you're getting inches in a day, it has much different consequence if you get the same amount spread over a longer period of time. Well, not surprisingly, in a warmer world, we expect, and what we see is ice melts, and all kinds of ice. We find that mountain glaciers and snowfields are melting around the world. Not everywhere, but many places. That's what's being shown here. It's time here, going towards the present. The lines are the length of the mountain glacier, and they're getting smaller. In other words, the glaciers, are the mountain glaciers and ice fields are retreating to higher elevations. We can also have more iconic images of this sort of thing happening. This is Glacier National Park. This is the edge of the ice field in 2008. A student sent me this picture, and where this marker is was where the ice field was in 1992. And you can make these projections. If the glaciers in Glacier National Park continue to melt at the current rate, they won't be there by the year 2030 or so. You know, there'll probably be some patches, who knows? But the point is that mountain glaciers around the world, and these lines over here are lines for mountain glaciers in the southern hemisphere, the northern hemisphere, close to the equator, etc. So numerous mountain glaciers are melting, and that doesn't sound like a big deal unless you're worried about renaming Glacier National Park, or unless you're an alpine skier. But actually, it is a bigger deal because many people, it's estimated billions of people, rely on the melting of that fresh water during the summertime when it's dry and warm to irrigate their crops and as a source of fresh water. I mean, even in California, the water source for the agriculture in California is coming from snowpacks in the Sierra Mountains. So, it's a much bigger deal than you might initially think with respect to the melting of mountain glaciers. But other ice sheets, larger ice sheets, are melting as well, including large sea ice sheets and ice sheets that are on land. This is the situation in the Arctic. So the Arctic ice sheet is not on land, it's covering ocean. And what happens typically there is it melts a little bit in the summer, and then it refreezes and melts and refreezes. But we've noticed the extent to which it's melting in the summer has increased. Now this line is the difference. This is the remaining ice after it's melted in a given season. And so the remaining ice after it's melted has been going down steadily. And we have the potential in the future, by the end of the century, to perhaps have an ice-free Arctic Ocean. Bad news for Santa Claus. We also see the other large ice sheets that are based on land. And so here in green, we have the ice sheet on Greenland. This is the mass of ice on Greenland through time going down, and here's the mass of ice in Antarctica going down. And these, if they melt, have the potential to significantly affect sea level. So these melting ice sheets, now Arctic ice is already floating, it's displacing its mass or its volume in water, so its melting isn't going to raise the water in the ocean, but melting the ice in Greenland, if you were to melt all the ice in Antarctica and add that water to the ocean, you'd raise sea levels by about 200 feet. If you were to melt all the ice in Greenland and add that to the ocean, you'd raise sea levels by about 15 feet. Okay, so it has the potential, I'm not saying this is going to happen in the near future, but it has the potential to strongly affect sea level rise, and it has the potential, melting of this highly reflective sea ice, to amplify warming. And this is what we call the the ice albedo feedback loop. Let me explain that. Maybe. There we go. So what's going on here is you have, the ice and snow are highly reflective. They reflect about 70% of the sunshine that falls on them. However, the water that gets exposed when they melt is not as reflective. It absorbs more sunlight. So we get, what happens is temperature rise, sea ice, Arctic sea ice melts. As the reflective ice disappears, darker ocean water absorbs more heat. That raises the temperature, and it amplifies this process. And we think this is why the northern hemisphere, where there's more snow and ice, is warming faster than other parts of the globe because of this feedback amplification or feedback loop. Okay, and then finally, I'd be remiss, given what's gone on this summer, not to mention that what we have observed is that the length of the fire season, at least for forests in the U.S., has gotten longer. And so we're seeing the wildfire scene increasing in many places. And this comes from the National Climate Assessment. But this is the cumulative area of U.S. forests burned over time. And they've done the calculation without climate change, but with the effects of climate change, the heat and the drying, it's basically doubled the area burned, and we've seen the effects. We've literally seen paradise burn. During the Camp Fire in California in 2018. In 2022, we saw the early fire season that happened in New Mexico and Santa Fe, and of course, this year, we're seeing the forest fires in Canada. This list, which you can't read, is not important. It's the four largest wildfires that have been documented, and they've all occurred in the last 20 years. And it's not just the fire, as you can all attest to, but the smoke that it generates also has an impact. So down here we're seeing the smoke wafting out of Canada across the U.S. in May of this year. And then of course we see in June and July, the effects on visibility in New York City. We saw it in Chicago. We even saw it in Morgantown. That's a water tower with a flying WV on it. Okay? But it's not just visibility that's important. The smoke generated by these fires has human health effects as well. And it's been, there's one study that estimates that the particulates from wildfires can result in 4,000 premature deaths in the United States each year and cost on the order of $36 billion each year in the U.S. So we have wildfires as well. So the time remaining, what I'd like to do is consider some of the challenges that climate change presents. And probably the biggest challenge is the difficulty to make the needed changes and our reluctance to do so. But it is clear, the old saying that if you don't change our direction, we'll end up where we're heading. And furthermore, the direction we're heading will take us to a place that we really don't want to go. And it was put fairly well by another person you should be aware of, who's Richard Alley at Penn State University, a very effective communicator of the science of climate change. And he notes that if we were to burn all the fossil fuels that are available to us, we can turn the world so hot that it gets hard to grow our food. We can possibly make it so hot that you can't go outside of your air conditioning without dying in some times and places. And he kind of sums it all up by saying, you do not leave your puppy in the car locked in on a hot summer day. So that's the direction we'd rather avoid. So if we want to avoid that, if we want to change our direction, what direction should we be heading? And there's disagreement about this, but the Paris Climate Agreement has set the goal of 1.5 degrees warming from pre-industrial temperatures, okay, as potentially a way of avoiding some of the worst effects of climate change. Lower would be better. Okay. And we've already warned 1.2. So what that means is we have to get carbon dioxide levels to about 398, and that doesn't really mean much to you until I tell you that currently levels are 417. So we have to reduce levels of carbon dioxide in the atmosphere, which means we need to be adding it at a rate lower than we're removing it. And it's also likely we're going to have to invent some equivalent of a CO2 vacuum cleaner to help Mother Nature in her cleanup. Sorry for the technical stuff. Can we get there? And I think the answer is yes, but we got a lot of work to do, and we don't have a lot of time to do it. And if I can get this stupid thing to work, there it is. So, this is what we've done. This is emissions of greenhouse gases. This is what we have to do to get down to that 1.5 pathway, 1.5 degree warming. By the end, this is all by the end of this century. This is what current policies will get us to about 2.5 degrees warming above pre-industrial levels. We have commitments to 2030 that might get us another 1/10 of a degree below that to 2.4. Other pledges, optimistic targets could get us down to 1.8 or so. And it's not just one, we can't just do one thing. We've learned that as well. It has to be many things that we need to change to get where we need to go. But we have the tools, we have the technologies, and we have sufficient understanding currently in place to get a really good start. And the other good news is we've already started. You just look at the hills around West Virginia with the windmills, and look at the solar holler and the installation of solar panels on people's houses, etc. And one tool that I want to introduce you to, because you can explore this on your own, if I've thoroughly depressed you by now. This is a tool. This is a computer program that's on the web. You can run it on your iPad. You can run it on your computer. You can't run it on your phone yet. It's out of the management school at MIT Sloan. They have spent decades working on it, and they continually update it. It's called En-ROADS. And I think that En-ROADS can help us make inroads in terms of figuring out what we can do. And what I wanted to show you here is you can get in here and it shows you where we're heading, and then it shows you in real time the consequences of various actions we take. So just to show you we could get to 1.5 degrees warming, I maxed out, put a price on carbon. That's one of the more powerful levers, as it turns out. We're going to max out energy efficiencies, both transportation and buildings. We're going to max out electrification. Here's my pointer again. Electrification of buildings and industry and transportation. We're going to really slow down deforestation. we're going to reduce emissions of other greenhouse gases like methane, and we're going to plant forests where there aren't forests. Now, if we do all that, we can get to 1.5. If you tweak other things, we could even get it lower than that. But you can play your own. This isn't the only pathway to where we want to go. And it's a powerful tool because you can find your own. Let's say I don't like putting taxes on things. Okay. How far can you get if with just energy efficiency, low-hanging fruit, that sort of thing? And you can see what the consequences of those are. And I encourage this group sometime, they have educational materials as well, so you can role play. You can be China, you can be India, you could be the United States, and you could negotiate different policies. And then you can see in real time what effect and how good or effective those policies may be. And there's a ton of information here. You can dig down, you can fine-tune it, you can read the assumptions, you can change the timing and the assumptions in this model, but I encourage you to explore it when you have the chance. And I have the website here. If you want the website, I can give it to you afterwards again. But if it's called Climate Interactive, and if you Google that, that'll take you. They have some other models as well, and this model is called En-ROADS, E-N-ROADS, R-O-A-D-S. Goodness. And this is the point where the speakers always dread, because it always comes up, but what can I do? And I'm going to sort of cop out and do what Richard Alley does, is don't ask me, a poor college professor who studied forests and happens to learn a lot about climate because climate turns out to affect the things that I study. But if you want some suggestions, perhaps you might take the advice of the theologian Friedrich Buechner, who says, follow your own path. But find where your greatest joys, the things that bring you the greatest joys, no matter what they are, meets the world's greatest needs. Then go to that place and do that work. And it turns out that climate change is entangled with so many of the world's greatest problems. Hunger, poverty, social justice, raising enough food, other environmental changes, loss of species diversity, urban planning, all that stuff. If that's your passion, go there and do good work, and it's likely going to help the environment. Another suggestion would be mindful of what's going on. Pay attention. Don't tune it out. There are, but I should say, be careful where your information comes from. For the most part, I think that the people who shout and scream the loudest in opposition to even talking about climate change or doing anything about climate change, in general, they're very good people with a strong passion, but they have some of the wrong or a lot of the wrong information. But having said that, be also aware that there are people and there are organizations out there that have and that are going to continue to intentionally mislead you. Once you become comfortable with some aspect of climate change, or maybe more of it, then you might become a trusted source of information for other people. But if you do that, my suggestion is do not shout it at them. That's the fastest way to get people not to pay attention to you. But rather, metaphorically, or maybe even actually sing it to them. Present it in a way that might resonate with them, that they might hum along, that they might retain and be more receptive to. You might try using various force multipliers. You can vote. And don't underestimate the power of voting, especially in this election that's coming up. If you don't believe me, Google Project 2025. And you'll find that there is right-wing, hardline conservatives that are formulating a war plan out of the Heritage Foundation that is going to basically try and undermine any progress that we've made, and you can read more details about it. So you can vote. You can adhere to the slogan of the Homeland Security Department. If you see something, say something. You can communicate with others. If you have the stomach for it, I personally do not, but if you have the stomach for it, you can get on social media and amplify your voice. Certainly others do. What can one person do? Don't be one person. And you're doing that right now. You're joining an organization, you're part of a group that's thinking about these things, that's talking about these things. You can write editorials, you can communicate with decision makers, but above all, be creative. Take your talents, your interests, things that you can do, and do something outside of the box, because that's likely to get noticed. And finally, let me leave you with some insights from a moral philosopher who's very thoughtful and writes very eloquently about climate change and the morality that's going on about the issues of climate change. And she notes that one of the things that just freezes people in their tracks, okay, is that they can become paralyzed by either blind hope or blinding despair. It prevents you from doing anything, and doing nothing is the surest way to not accomplish anything. By blind hope, I mean everything's going to be all right. You know, things go up, things go down. The invisible hand of the marketplace will work it out. The invisible hand of the Almighty will take care of us. Government will look out for us, whatever it may be. Okay? So don't worry, be happy, and I don't need to do anything because it'll work out. So that's blind hope on one end. On the other end of the spectrum is blinding despair. This is too overwhelming. There's nothing I can potentially do that will make any bit of difference whatsoever, so I don't need to do anything. And she points out that's a false choice, that's a false dichotomy. Because on either end, what you're doing is moral abdication. You're not taking responsibility because it's going to work out fine, or, there's nothing I can do. But she argues that there's a rich moral middle ground, which she calls living with integrity. And what she means by that is simply living with a consistency between what you believe most deeply in and the way you live your life. And most people will believe that the earth is a good place, that we want to leave a world as rich and full in possibilities for our children as we inherited from our parents. And by doing good things, by believing those are good things, and making them consistent with the way you live your life, it will make a big difference with respect to climate change. And I want to finish by reading just a section from a book she's written called Take Heart, Encouragement for Earth's Weary Lovers. And she has other books that I can recommend to you as well, but hopefully this will leave you a little bit uplifted. Okay, she says, in aggregate, over time, around the world, individual acts taken all together have an exponential effect, feeding on themselves the way fire creates the wind that powers the fire. What lifts my spirits is knowing that positive change works the same exponential way. If the earth makes the great turning, it will not be because of one xeriscape front yard, plus one wind turbine, plus one local farm, plus one redesigned cook stove, and on and on. It will be because imagination creates more imagination. Good creates more good. Respect for the land creates more respect in a swirling whirlwind of change that sweeps away business as usual and upends the culture of reckless exploitation. Even as we approach a tipping point in runaway climate change, we are approaching a tipping point in the human conscience. What has been astonishing indifference has become a worldwide movement for climate justice and ecological wholeness. We have met the enemy, and he may or may not be us, but we have also met the change makers, and they definitely are us. And I think all of you in this room today fall into that category, and I thank you for your time. I can try and answer questions, or we can have a little discussion if you wish. Yeah.
Have you considered the polar shift idea? And number two, what about China, who does not, does a lot more, and so are you taking this statistic, are you counting China in there as part of the reduction of your percentages or no?
So, if you're talking about that model of how we get to 1.5, does that include China? It includes, it's saying globally we have to do this. How you negotiate that between countries, people have thought about that as well. What is a fair and equitable way of doing this? And that's kind of another kind of distraction that gets thrown in the way of making progress, is like, we're not going to do anything unless China does anything. It's not fair. Well, you can look at that in a variety of ways. We, for a long time, were the leading emitters of greenhouse gases. Now it's China. Okay, maybe they should play, have a bigger role to play. But if you put it on a per person basis, we're still about twice the per capita per person emissions. So maybe it's not fair. What about countries like India or others who need to develop and haven't really contributed very much at all to this? I'm not sure I'm addressing your question. In terms of the polar shift, I'm not quite sure what you're talking about.
Okay, the whole part of this climate change, the things that we're seeing now, is what they're saying is that the shift, this axis, polar axis, is shifting at so many points per decimal per year. So they say that's contributing. They say it's a natural phenomenon. I don't know. I've researched it totally. I've read a little bit about it, and they say that's contributing to the runoff of this stuff. So if you consider that,
so I think in the graph I showed you, which is from probably the most authoritative source of information, is called the Intergovernmental Panel on Climate Change. This has been going on for decades. They do kind of every 5 years a reassessment of all the scientific, or a lot of the scientific literature, and they bring in governmental representatives as well, and it's a big long process, and I can't summarize very well for you, but you certainly can find a lot of information about it. The graph with respect to natural causes versus human plus natural includes things like wobbles in the Earth's orbit around the sun. It includes things like volcanoes erupting. It includes those natural processes. So I think the answer is yes, that the scientists who do this stuff, I don't, but that do these modeling exercises and examinations have tried to go through the whole checklist of other explanations. But the only one that really drives it is the increase in greenhouse gases. And actually, I'll leave this up here. I have one more slide, which you can't see. But if you come up, there are a bunch of websites of places where the information I think is pretty good, and other people. And you can come look at it on the screen afterwards, and I can show you. One other thing in terms of websites, there is a website called Skeptical Science. It's on here, Skeptical Science. And that website tends to address a lot of critiques that people throw out about, it's the sun, it's not us, it's this thing. And the good part about it is they usually link to the scientific literature. They have their explanation for why that's not really accurate. I mean, scientists have been at this game for a long time, sort of rebutting arguments that keep coming up, that keep coming up, that keep coming up. And frankly, it's gotten to the point of, yes, there are useful things to think about, important things to think about, but it's getting to the point in some people's hands that it's used as a stall tactic. Yeah.
So in one of the early slides, you had the graph of the glacial periods and interglacial periods, the rising temperatures and,
Right.
and the rising CO2 rates.
Do you want me to try and show it again, or?
Well, no. The thing that's interesting to me is that you didn't speak to, that I wondered if you could clarify a little bit, is that from each glacial to interglacial period, both temperature and CO2 drops precipitously on the graph, right? They kind of
Right.
build up slowly, both together, and then they fall off a cliff. Why is that?
Oh, so why is the end of an interglacial it's more steep than
Yeah.
the
Do we know what the triggers are?
well, there's a lot of ideas about the triggers.
The reason I ask that is it seems like that might be your range of getting on top of rising temperatures and rising CO2 rates if we understood the natural processes.
Right. So, I mean, people, especially a group at Penn State, kind of has looked at these things. So, what causes those oscillations? We know what triggers them, and it actually turns out to be wobbles in the Earth's orbit around the sun. The fact that the Earth is sort of tilted on its axis of rotation, and about every 41 years it sort of does this and back, and it's periodic. And it also, its orbit around the sun goes from being a little more circular to a little more elliptical. So there are times, and then there's another thing called precession, where the seasons occur in this. And when you get the time, there was a guy named Milankovitch who did these calculations long ago, and he said, once your observations catch up, you'll find, that there's going to be these cycles in climate. And once we got good enough data, we actually found those signals, a 41,000-year signal, the dominant signal that you saw is a 100,000-year signal. And the interesting thing is that the forcing from the orbital wobbles of that particular signal is the weakest of all of them. And so they had to explain why the amplitude was at 100,000 years for a long time, or the periodicity for 100,000 years for a long time, and why it happened. If you just believe Milankovitch, it would be only sort of a northern hemisphere phenomenon. But why is it happening synchronously in the southern hemisphere? So you need something to amplify that signal and carry it globally. And we think that's what the CO2 does. Now, what causes it to go down? There's part of that is an ice albedo feedback. Once you start, the trick with all of that is keeping the summers in the northern hemisphere cold enough that the snow that fell doesn't completely melt. And then you start to accumulate, and it turns into big ice sheets, and the ice sheets move under their weight and advance. So the ice albedo feedback will amplify that somewhat, but it can't account for the whole signal. What's drawing down the CO2, and there's all sorts of hypotheses about that. A lot of them have to do with storing more carbon in the ocean, because the ocean circulation seems to be an explanation that will operate on that kind of time scale there. Now, going back further in time, going back millions of years, some of those rises, a lot of that was driven by a greater tectonic activity. You have a long period of time with more volcanoes spewing out more CO2, and then it rises and warms the world. Okay, and that's driven by CO2 being released by volcanoes, and then it slides down because there's this fascinating, when the volcanoes get quieter, it draws down because there's this fascinating thermostat that's called the silicate weathering thermostat. In other words, the CO2 will make a weak acid that reacts with rocks, and that can scrub out the CO2 over long periods, and it's very slow. Okay, and so that's what would draw down. Whatever we burn, if you wait 500,000 years or a million years, that'll ultimately return it back into really shells in the ocean that then sink to the bottom. I don't know if I probably didn't answer your question. Just hammered a lot.
No.
So,
That's
you
right.
have a lot of good information in your slides that we couldn't really
See.
get to. Would you consider making that available, like through the library somehow?
Sure. Okay, sure. Yeah.
I have a question. I think I heard you say earlier that aerosols help. And, you know, you were told years ago, don't use aerosol. Maybe we should all go back to using aerosol hairspray. Are there things?
Right.
Are there things like that that we can do that?
Yeah, and these ideas have been put out. So it's not aerosols from your spray can. Aerosols are fine droplets of either solid or liquid droplets that are small enough that they stay suspended in the atmosphere. Okay. Way back when, there were aerosols that were emitting chlorofluorocarbons, and they were just responsible for depleting stratospheric ozone. But there are aerosols, particularly sulfate aerosols, that are shiny, that reflect light. So it's increasing that shininess, or the splash in our kitchen sink model, the reflectiveness. And they have a cooling effect. And we can see them in the record. When Mount Pinatubo erupted in 1991 in the Philippines, globally the temperature, it was such a strong eruption, it injected sulfur gases into the stratosphere. They turned into sulfate aerosols that reflected light and got carried around the world, and it cooled the planet by a half a degree or a degree for about 1 or 2 years before they got scrubbed out. People have looked at that and said, well, people, especially and serious scientists, have looked at it because they're so pessimistic about us doing anything to reduce emissions. They've done calculations, and some people call it the human volcano. Maybe we can take guns and shoot up sulfur gases and particles into the stratosphere and cool the planet. There are issues that we don't understand in terms of what that would do. I mean, fundamentally, think about, okay, who gets to control the thermostat of the Earth? China, Russia, us. And then, the other thing is the greenhouse gases. If we just only do that and still burn, they're accumulating, and the high levels are going to stay there for 100 years, 1,000 years. And when we stop doing that, the aerosols come out of the atmosphere fairly quickly. And now you've got, a ton of extra CO2 in the atmosphere, and you haven't really solved the problem. So people have thought about space mirrors will reflect, sunlight back there. We're probably better off thinking about ways of getting alternative sources of energy and reducing our emissions, and a lot of the issues that are associated with that. I'll hang around afterwards. But,
do you find in your conversation about Industrial Revolutions, especially the second Industrial Revolution, when you discuss identifying the carbon isotopes that are related to that period, it convinces more people that that industrial piece is from us?
I have that slide. I didn't put it in.
I think that's pretty convincing.
So let me say a few things. So the issue is one of attribution. It is, why are we to blame? Okay, and you can make the argument several ways. One is timing. If you look at the rise in CO2, it corresponds with the Industrial Revolution. Okay, and we know what went on there. The second is kind of quantifying. If we can take industrial records, we know how much coal or oil is burned and their composition, and we can estimate how much, and people have done this at Oak Ridge and other places, how much CO2 has been added to the atmosphere, and it's more than enough to account what's been observed. If it had been less than enough, then something else is going on, but it's more than enough that account for it. Another aspect, or beyond the timing, beyond the, we've added more than enough to account for the observations of rising CO2, are chemical signals that are present in the CO2 itself, and that's what you're referring to. So There are isotopic signals, and an isotope or atoms of a given element that have the same number of, sorry about this, protons, but different number of neutrons. So they behave chemically the same way, but that slight difference in mass gives them some unique properties that we can detect. And what we see in general is, one thing we see is called the beta effect. It means, what we see is that the amount of radioactive carbon in carbon dioxide in the atmosphere has gone down, and the timing of that is it goes down, and it starts going down at the about the late 1800s or so. And the reason why it goes down is because of the burning of fossil fuels. Why is that? Fossil fuels, coal may be 300 million years old. It has no radioactive carbon in it. The half-life of radioactive carbon is 5,730 years. By the time you get to 10 half-lives, you're nowhere near 300 million years, and you have no radioactivity. So what you're doing, it's like you have a pitcher of iced tea, and you start pouring water in it, and you start stirring it around. What happens to that iced tea? It gets weaker and weaker. And so as we pour carbon dioxide into the atmosphere that has no radioactivity, the concentration of radioactivity in that CO2 in the atmosphere goes down and down. So that's one effect. And then there's another isotope that's a stable isotope. And what we see there is that the carbon that we're burning has a kind of a distinct signature, and the signal in the atmosphere is getting more and more like the fuel we're burning through time. It parallels, as that signal, I forget which it goes up, goes down, and the CO2 emissions goes up, and it's almost a perfect match. So that's usually kind of the nail in the coffin with respect to attribution, along with the modeling exercise of, including everything else we know, and it doesn't reconstruct what we've observed until we add in human emissions of greenhouse gases.
One more, I know Sean will probably kill you, but what's your take on the recent Avon discovery, the possibility that?
Well, you saw that region in the ocean that was cooling rather than warming, and there are very respected climate scientists who argue, Stefan Romsworth in particular, that argue that that's a result of a slowing of this ocean circulation that carries a lot of heat to high latitudes, and when it cools off, it releases that heat to the surrounding. And we're talking an amount of energy that's I forget the calculation, but it's about 100 times or more the amount of electrical energy production for the entire world being released in that location. And that in part is why, even at higher latitudes, the climate's a little bit warmer than you'd expect. And if that slows down and stops transporting that heat to those latitudes, it can have a strong cooling effect. This is the premise of, what was that movie?
Day After Tomorrow.
Day After Tomorrow. No, we're not going to return it to another ice age, but that was sort of the premise to the Day After Tomorrow movie. I guess we got to be out of here, right?
Thank you.